Good day, folks. Welcome to Bright's Mind Academy, where we bring brilliance to every lesson. Now, in today's video, we're going to be looking now at a topic called momentum and impulse. Okay, so this is a topic that is now assessed in grade 12. Okay, we find this topic in grade 12. All right, now before we move on, we're going to move quickly because now this topic it is a very straightforward topic now. Okay, so what first I'll introduce is now what we call momentum. Okay, I'll first introduce what is momentum. Now, by definition or per definition, we say now the momentum, it is the what? The product of the mass and velocity of an object. Now, the definition itself can now derive a formula. Now we are saying momentum, it is the product of the mass and velocity of an object. You can put your English nicely on, or maybe say the product of the mass and the object's velocity. However, you want to put your English. But now the important part is now your momentum. Your momentum, it is now the what? The first keyword, it is the product. Okay? Of the what? Of the mass and velocity. Okay? Of the what? Of the object. Okay? Not object. Object. All right? Now we can derive now a formula for that one. Now, momentum can be thought of as a quantifying the motion of an object, right? So we say now momentum P, it is equal to mass multiplied by velocity. Okay, where now we say P, it is our momentum, where we say M, now it is our what? Our mass, or some call it mass. Mass, it's fine. Now, last one, it is now what we call the velocity, not the speed, okay? The velocity. Now, we know that mass is measured in kilogram, right? Mass is measured in kilogram. Then our velocity is measured in meters per second. Like that. I'd prefer writing it like meters per second. It's fine. Okay. So now this gives us an idea on what the SI unit for momentum will be. It will be now kg multiplied by meters per second thereof. So for momentum, it will be kg multiplied by meters per second. Or you can just say kg meters per second. Like that. Okay? Yes. Either way, it's fine. Now, I want you to take note of something. This is a vector. Okay? This now quantity here, this quantity V here, it is a what? A vector. A vector. Okay? So now what does this have to do with us being a vector? So now it is a vector quantity, so it will influence now the what? The momentum. Okay, therefore we say now momentum also is a vector quantity and has both magnitude and direction. Okay, it is therefore important now to always include direction in all momentum calculations, because now we are saying what this is also a what? A vector. A vector. So it is a vector due to this mass, so to this velocity. So always, okay, let me do this. Let me say this, okay? Momentum, where can I note this? Let me do this. Okay, let me say it is a vector, and always in the direction, always in the direction of the velocity. Am I right? Yes, of the velocity. Bear in mind, I'm still talking about momentum. Okay, momentum is a vector and is always in the direction of the velocity. Okay, yes. Now we are talking about the momentum now. Okay, here we are talking about momentum. Now let's have an example now about momentum. This should be a fairly straightforward thing. Momentum, we are moving fast, cruising nicely on it. Okay, let's have an example. Let's say now, on our example now, we have okay, let's say a golf, or a golf ball of mass 0.05 kilogram. Even if you are to be given this in grams, you have to convert it into what? Into kilograms. Leaves a golf what? Golf club at a velocity of 90 meters per second in an easterly direction. Now, this is very important because you have to be given now the direction of the velocity, because now we are referring to the velocity, not the speed. Now they say to us, calculate the what? Calculate the momentum of the ball. Good. Now this is very important. Why? Because now from the information we are given the what? The mass of the golf ball. We are also given a velocity. Okay, and we are given now also the what? The direction of that velocity thereof. Therefore, this is fairly straightforward calculation. You are saying P, it is equal to mass multiplied by velocity. Our mass, it is 0.05. In this case, multiplied by what? By 90. Then this will give us something like 4.5 what? Kilogram meters per second. Hence, remember this is a dot. Okay, it shows you it is a multiplication of the what? Of the mass as well as the velocity. Okay, yes. Where? East. Very important. Very important. Now you do not include east, you lose a mark. So it is a mark for a formula, mark for substitution, mark with the direction. Include direction. Okay. Now I want you to take note of, let's make an example of now what you call a momentum. Let's say you are a sprinter now, you are a boys under 12, you are running now in a race of 100 meters. Therefore, you are running now. Remember, as a person has a mass, right? A person has a mass, and now you are the one running. So you have a velocity. Why? Because you are heading in whatever direction that you are heading to, right? Now, this is what we call now, we say, okay, that particular sprinter runner has a what? Has momentum. Why? Because the sprinter itself has a mass, and now he or she is running at a particular pace, which we now refer to it as what? As velocity. But now there is this instance. What if now that the runner during the run or the sprint or the whatever, the race, the runner get tripped? Let's say now the runner trips now, and then has to move slower, because now remember, if you're moving fast and you get tripped, what will happen? There will be a change in what? In velocity. Do we agree in that there will be a change in velocity? And remember, that the mass of a person does not change. So if now the velocity changes, how will that influence now the momentum? It means now we will have what we call now the change in momentum. Okay, it means now we will have what we call change in momentum. Okay, why are we having a change in momentum? We are having a change in momentum because now the velocity has changed, right? Now, let's have another example. Let's say now when a moving object comes into contact with another, okay, moving or stationary, it results in a change in velocity for both objects and therefore a change in momentum for each. Okay. Now, change in momentum, okay, we'll have a change in momentum, okay, here now, this is just momentum, okay? It does not have any definition. Change in momentum now, it is equal to momentum final minus momentum initial. But I want you to show you exactly where do we come or from now this part, okay? Now, remember, this will have, we are still talking about what? Momentum. Remember, you initially had a momentum of a certain, okay? You had a momentum initially, you were sprinting at 100 meters per second. Now, you get tripped, now you have to run at maybe 82 meters per second. So it means there was a change in what? In the momentum in which you were keeping track of. Now, the final momentum can be say, okay, this is this is the mass multiplied by the velocity. Remember, we are still talking about the same object, the same mass here, okay? Mass multiplied by velocity final in this case. Why? Because now momentum final, it means now it has a what? Final velocity, because you cannot say mass final, mass initial. Mass the mass remains constant, right? Minus mass, then initial what? Initial velocity. Therefore, now we say now, okay, right. So now it means now our momentum, if we were to take out m as a highest common factor, therefore we get to realize that no. Remember what is this? Remember something final, a change, it is final minus initial. So now we say, all right, if now we have change in P, it is equal to mass multiplied by, what is this? This is what we refer to as change in velocity. Why? Because now it is velocity final minus velocity initial. Similar, can you see here? We say the change in P, it is P final minus P initial, right? Yes, that is what we said. So now we're having a change in momentum due to the change in what? In velocity. Okay? So this we say now it is a what? Change in momentum due to what? Due to the change in velocity. Okay, now please take note of this. Us saying now you have a change in momentum, it does not mean now you are running in different direction. Remember, you can be running from here. Let's say this is 0 meters. Then you are running to 200 meters. Now let's say from here up to this point, up to, let's say, 60 meters, you are running at a velocity of, let's say 50 meters per second. Then you get tripped by now a stone. Let's say you have a stone here, it trips you. Then do you agree with me that your velocity going forward now will differ? Your velocity going forward will change to maybe something like 35 meters per second. But can you see now you are still moving in the same direction? Yes, what we refer to is just that you had a change in what? You had a change in momentum. So it means now if we were to do precise calculation, we would say now, change in momentum now, it is now what? Mass final velocity minus initial what? Velocity. Okay, because now we have now what? And remember, okay, let's do this. Your mass, let's say this particular person had a mass of 50 kg. Okay, I think I'm going to use 10. Let's say 10 kg. So it's going to be your mass multiplied by final velocity is 35 minus initial velocity is 50, right? So this is going to give you something like 100 and negative 150 meters, so kilogram meters per second. Where, let's say this is east, okay, east. Now, oh, so for now, let's not talk about the east. Okay, remember if you are running east, this is your positive direction. Therefore, the negative direction is going to be your west. So now, can you see now the momentum that we get here? It is negative. So it tells us that this particular person slowed down. Okay, it does not necessarily mean that this particular person moved from here and after that change in velocity, after tripping, that particular person returned back. No, it's just that there is now a difference in the what, in the momentum, and since well the momentum is negative, it tells you that the momentum is acting in the negative direction. It's like that particular person is slowing down. Okay, because now why, that particular person tripped. Okay, so now your momentum will be opposing the direction, because if you trip, you'll want to do what, you'll want to stop. So your momentum is no longer going forward, it's now opposing your initial momentum. But now since when we have a bigger momentum, initial momentum, if we were to calculate initial momentum, our initial momentum will be 500 kilogram meters per second, and our final momentum will be a 150 kilogram meters per second. But now, since your initial velocity it is greater than the final velocity, hence now you are having, you still get to see that particular person moving where, moving forward. Okay, yes, this is just the concept of momentum. Okay, yes. Or another momentum that you can have is, now let's say uh you have a wall here. Okay, let's say this is what we call a wall. We refer to that as a wall. There is a person. Okay, this is a soccer star. Here is a soccer here, or a ball in particular. Okay, let me reduce. So let's say now this particular person kicks the ball. Okay, let's take east as positive, west as negative. Direction is very important when you talk of what, of momentum. Remember I stated that. Let me extend my wall. Now here's my ball. Let's say this ball has a mass of 0.5 kilogram. Okay, now this ball will move. Let's say the particular person kicks the ball towards the wall with a velocity of now 5 meters per second. Now I want us to realize something. As this ball now reaches, okay, I'm gonna change the point. I know it's gonna go there and come back, but for the purpose of explanation, I'm gonna say here is the ball. Okay, here is the ball. Okay, so now we kicked the ball towards the wall, and now do you agree with me that the wall had a what? The wall had a contact with that ball. Okay, okay, yes, the wall had a contact with that ball. And remember, what do you remember about now? Two objects now a colliding. Remember, if two objects meet, it means now Newton's laws now will come into now into play. Okay, then now the ball will move now in the opposite direction. Here is that ball moving now in the opposite direction. But do you agree with me? As the ball hits here, the ball will not return with the very same velocity. So now let's say our ball returns with a velocity of 3 meters per second. Can you see that? Can you see that? Now the ball was kicked towards the wall in an easterly direction. Then the ball had a contact with the wall. The wall then compressed the ball towards back to the to the uh, to the person who kicked the ball. But now the velocity now will be lower. Okay. Yes. So now this is also now an explanation of what we call now change in momentum. Can you see now the initial momentum was in that direction? Can you see now the initial momentum was something like 5 multiplied by 1, it is 5, something like 2.5 kilogram meters per second east. Okay. But now, can you see now the final momentum is going to be what? Let's say it's positive. But can you see now the momentum is going to be what? Okay. Let's do this. Since while this ball is moving in that direction and we chose east as positive, so this is going to be positive. This one is going to be what? Is going to be negative. Why? Because it is moving in an opposite direction. So now when we say now P, change in momentum of this ball, it's going to be final velocity minus initial velocity, okay? Therefore, what is my mass? My mass is 0.5, then my final velocity is -3. Can you see that? Can you see that? -3 minus what? Minus final velocity. So my final velocity is -3 minus of the formula. Initial velocity is what? It is 5. Okay. Then I will have something like -8 multiplied by 0.4, which is -4 kilogram meters per second. So therefore, this tells you that your change in momentum, it is equal to 4 kilogram meters per second where? West. Okay. So this should be very, very important thereof. Okay. This should be very important thereof. Yes. Now, I want us to talk now Newton's second law in terms of momentum. Okay. Newton's second law in terms of momentum. Now, do you agree with me that this ball here is giving what? Is giving what? The net force. Remember, without the net force that you are giving this ball, there will be no movement. Okay? So this particular footballer or whatever, this particular person gives now the external force to this ball, which we now refer to the air net force to this ball. Okay? And by doing so, this will cause this ball to do what? To accelerate. Okay. So as the ball accelerates, it accelerates towards the what? Towards the wall. Okay. So now we have now another concept now that we call now. Where is my okay? Newton's second law. Newton's second law. Let me just say second law in terms of momentum. Okay. What does Newton's second law in terms of momentum states now? Okay. Now remember, I just said the particular person should now do what? Should give the ball the what? The net force, so that the ball can do what? Can accelerate in the direction of that in the direction of the motion. Okay. So now when the net force is changing, can you see when the net force is changing here? Can you see it's so we're gonna give it a net force here, right? Of a certain amount. As it reaches here, the net force changes, right? Because now it has a net force moving in that direction, but now it has an opposite force that opposes it. Okay, so now there will be a change in the what? In the net force. So is the velocity of it. Okay, remember when now I'll do this. Okay, I'll come back to that. I'll explain that because yeah. This is where we are gonna be heading to. Okay. So I want you to see this. If you are given this ball now, okay, let's explain this. Newton's second law in terms of momentum, it says to us the net force acting on an object is now equal to the rate of change in momentum of an object in the direction of the net force. Okay, so now Newton's second law says to us the net force acting on an object, okay? The net force acting on an object, okay? Remember, I'm saying you are giving the ball, you are applying a force on that a ball, right? So it's going to have a net force because it's going to experience the applied force as well as the frictional force, right? Those are acting horizontal. But either way, the net force will be towards the direction in which you kicked the ball to. Okay, why? Because now you applied force, we assume that it is bigger than what that friction because I mean it managed to move, right? Now we are saying that net force is equal. Can you see that is equal to the what? To the rate. Remember, the rate is divided by time. To the rate of change in momentum of an object in the direction of the net force. Does it make sense? Now we are saying that the net force that is acting on that object is equal to the rate of change in momentum. Now, the rate in which our momentum changes as it moves towards the wall or whatever, okay, in the direction of the net force. Let's say now we are having our ball being kicked there. Do we agree that at the end of the day, this ball will come to rest here? Because why? Because now, as it moves with that applied force, there is what? There is friction opposing the motion. So hence we are saying the net force acting on an object is now equal to the rate of change in momentum. As the momentum changes, remember the momentum will decrease now. Okay, the momentum will decrease. Why? Because now the momentum will want to move in the opposite direction. Why? Because now our net force will now will come to zero. Our net force here will come to zero. Why? Because it is at rest. And remember, at rest, acceleration, it is equal to zero. Okay? So now, so is our momentum. It means now as my net force is decreasing, as I go there, my net force is decreasing. So is my what? So is my momentum. My momentum is decreasing. Why? Because now, actually, my change in momentum is decreasing because now my initial is going in that direction, but now my final is going in that opposing direction. Remember now, I'm slowing down. So it means now momentum wants to move in the opposite direction, momentum final. Okay? So now, let's have a derivation of this. Let's say now, remember I'm saying now you are giving that object a net force, right? So it's gonna be like this. This object, you're giving it a what? A net force, and it will do what? It will accelerate in the direction of that net force. Okay? Now, but now remember what did we okay, from grade 10, what do we refer to momentum, sorry, acceleration as? Now you agree with me that in grade 10 and grade 11, if yes, your teacher reminded you of that, we said now acceleration, it is the what? The rate of change of what? Of velocity. So yes, the rate of change of what? Of velocity. Remember, every time when you say the rate, it is divided by the time. Okay? The rate of change of what? Of velocity. Okay? But now, I want you to see this. If I'm having this, what is this quantity here? mass multiplied by change in velocity. What did we say that is? Remember from here now, we said now, change in momentum is final momentum minus initial momentum. But now as we manipulated the formula, we got that this is mass multiplied by final velocity minus mass multiplied by initial velocity, which is in this case now what? Mass into final velocity minus initial velocity, and we said this is what we refer to as the change. So do you agree with me that mass multiplied by change in velocity, it is now referred to what as change in momentum? So in place of putting m change in v, which now we remember that this is mass final velocity minus mass initial velocity, or you can also manipulate it further and say mass final velocity minus initial velocity, like that, right? So we just said, okay, this quantity we know it is what? Change in momentum divided by change in time. Now let's rewind back to the what? To the definition. The definition says now to us the net force acting on an object, okay, which is this one. It is equal to the what? To the rate. Remember the rate, it is what? Change in time. Divided by change in time. It is equal to the rate of change of what? In momentum of an object. Is it true? Yes. It is equal to the rate which is divided by time of what? Of momentum. As we did mention with acceleration, that it is the rate of change of what? Of velocity. So now we are saying now F net momentum in terms, Newton's second law in terms of momentum is now the net force acting on an object is equal to the rate of change in momentum of an object, where in the direction of the net force. So all of these will be happening where in the direction of the net force. So now I want us to have a very nice use of Newton's second law in terms of momentum. All right. Before we now move on to another concept, use of Newton's second law in terms of momentum. Okay. How now these work in now real life situations? Okay. Now, I want us to remember this formula now. We say now the formula says F net, it is equal to change in momentum divided by change in time. Okay. Now, I want you to know something. As in life, we want now our momentum to be constant, our change in momentum to be constant. What do I mean? Take an example. Now, let's say you are a student, right? You are a grade 12 student taking now physical science, right? You know that physical science can be a little bit tricky and challenging sometimes, right? I'm not saying it's hard. It can be challenging, right? But you know that you are passing with 80% your physical science. You are passing physical science with 80%. Now, what you want to do here, you want to maintain this momentum of getting 80%. Okay? You want to maintain the 80%, meaning now you do not want your 80% pass to change on physical science on whether to be 70s, 50s. Well, you'd want it to be 90s or 100 possibly. But now this is good for a grade 12 learner. So you would rather want to maintain it. So where am I going with this? So now we have applications of Newton's second law in terms of momentum. Now where we say now, we want to keep this momentum the same. Okay? We want to keep, let me say, we want to keep the change in momentum constant. Okay, so now remember, if we keep something constant like this one, it means now there should be a relationship between this one and that one. Now we know that F net is directly proportional to change in momentum, right? Because if this one increases, that one also increases, right? And we can see that F net, it is inversely proportional to what? To change in time. So now what does this mean? It means now if my time is increased, if I increase my time, it means now my net force will do what? Will decrease. All right. Now we have many concept now use of momentum. Okay. Let me name the first one. Tennis. Is it tennis? Let me say now. Is it tennis? The one that has a sticker like this, and the ball, they bat, like, what do they call it? Mm, cricket. Yes, cricket. Cricket or tennis? I'd say cricket. Okay. Now, how does Newton's second law in terms of momentum now apply in cricket? Now, I'm going to write this out. For now, I want you to listen very carefully to me. When there are two people here, let's say this is a net, right? I'd want to draw that in 2 dimensions, but I'm not a good drawer. One thing for sure. Okay, there is this person here and this other person on the other side. Okay, they are holding their things that they use there. As they are playing now, the ball, as it is now projected towards the other person, they're off. Now we are talking physics. As it is projected towards the other person, I want you to see something. This other person does not take this, I don't know what they call this, and I'm sorry. They do not take this, for now I'll call it a stick. Okay, let me use an example with cricket, okay? I don't know, they call them the wicket, the what? I don't know. Okay, let's say here's that particular person holding that sticker, not sticker, stick, okay? Then here we have the poser, the one that throws, okay? I don't know what they call that. This particular person is having that little ball there. So this ball is gonna be what? It's gonna be thrown to that particular person, right? Now, this person, the person who's supposed to be now hitting that ball, if you realize, if you have ever watched cricket, this particular person does not take the stick, the sticker, the stick, and move it towards the ball, but rather this particular person takes the stick and move it backwards. Okay, the particular person takes the stick and move it backward so that he can do what? He can beat the ball. Can you see? He starts forward, at the backward, and now does what? And bring the stick forward and does what? And hit it, instead of doing what? Of instantly taking the stick towards the ball. Why is that helpful now? Remember, for the same, we are assuming we are under the same momentum. Change in momentum is constant. Okay? We are assuming that we are living under the constant momentum now. Now, as now the ball is on air, if the stick is moved backwards, do you agree now the contact time between the ball as well as the stick will increase? Now we are increasing the contact time. The change in time will increase in this case. The change in time will increase because if he met the ball here earlier rather than waiting for the ball to reach here, the time will have been slower here, faster, or rather here. Faster, the rate at which the ball reaches here will be now slower. It means now the time taken from here to here is much slower than the time taken from here to there. Okay, so now or rather this person taking the stick backwards is now increasing the time in which the ball spends on air, right? So now, according to this relationship thereof, this momentum relationship thereof, provided that this is constant, okay, constant. What happens if now I increase my contact time? If I increase my contact time, what will happen to the net force? We agree, remember we said now the net force and changing time are inversely proportional. So what will happen? So you agree with me that the net force will decrease. So that is what we want. We want now the ball not to hit us hard, because if the ball were to strike the stick with a greater net force, now it will cause damage to the hand of that particular person who was supposed to be hitting the ball, right? So instead, we'll say, okay, let's try to reduce the force that this ball is coming with. But how can we do that? The only thing that we can do that is that, remember, the momentum is the same, okay? What will happen is that, okay, let's rather increase the contact time by doing what? By taking the stick and moving it what? Backwards. So you understand that? Yes. So that is how we apply now the relationship of what? Of a momentum in terms of Newton's second law in terms of momentum, rather. Okay. Yes. Another one. Okay. Let me make them two. Okay. Because they like to play within these two ones. They say the other one is now airbags. Okay. Airbags. Have you ever heard of an airbag before? I believe so. Remember, an airbag is what the cars now, modern cars have. Now, remember, modern cars have airbags such that collide, when you collide with something, now what happens to the airbag? The airbag now puts in front of your face. I guess. What now? The question is, what is the purpose of that airbag? Okay, we'd say now the purpose of that airbag, it is to protect you from hitting the um, the window, maybe, or from hitting the steering, what do you call this thing? The English, the yeah, the whatever. Okay, but now the actual fact is that now the airbag now, if now this is a wall and you are coming with your Mercedes Benz, of course. Okay, cruising nicely. Okay, I don't know how to draw. Let's say here you are. This is a chair. Okay, here you are. Okay, I don't know how to draw. This is a steering. When now here you are, relaxed. Of course, you are sitting. Okay, you are driving there. Okay. Now, when you collide, during collision, what happens is that the airbag, as the airbag now comes in front of your eyes, it will now, remember, the airbag will not stop you from hitting the screen or or the the steering, or the stair. I don't know what you call that in English. Mara thing to drive wheel. Okay, it won't stop you from hitting that, but rather it will uh, appear in front of your face. This is what you refer to as an airbag. It will now appear on your face. I don't know the proper English to use. It will push in front of your face, right? But now, what does that help you with? It helps you to now to take you back. Okay, the airbag will take you back, because now remember, the net force is still in that direction. Fnet is still in that direction, okay, as well as your acceleration is in that direction. So now the airbag will move your face a little bit backwards, but still your momentum, since well now you are having the net force that is going in that direction. So now your face will be moved a little bit backwards, but it will still continue moving forward. But now, can you see now, we reduced the time in which you reached the windscreen, okay? Because now, without an airbag, immediately after collision, you will have went directly straight to the what? To the windscreen, okay? But now, since when you had a what? You had an airbag. It reduced it increased the time in which you reached the what's this? The windscreen. So now, remember what do we say again? If now the airbag reduces the contact time, if now the contact time is reduced and change in momentum is constant, what will happen to the net force? So our contact time is increased because now you take longer to reach the windscreen. What will happen to the net force? We agree that our net force will do what? Will decrease. And how does that help us? It will help us to, okay, hear me carefully. Because you will get hurt, you will be damaged. But now we are this airbag, since when it increased the contact time, it will rather reduce the damage. All right, it will reduce the damage that will occur to you. Yes, the damage should happen because you are reckless, right? But now it will do what? It will reduce the damage that you are supposed to feel eventually before. Okay, so that is the use of now airbags, and this is where now Newton's second law in terms of momentum comes. Okay, let's make an example of an airbag. We'll say reasoning. The reasoning is the same for all cases, just that you have to put your weights nicely. Let's use an example of cricket. Cricket example, okay? So, no, arrest a bed. Not arrest a bed, airbags, okay? Now we'll say, the first thing that we'll say is that the arrest a bed will now do what? Mhm. So not the arrest a bed, the airbag will do what? The airbag increases the the contact time or impact time, which we now refer to as change in time. Okay, increases the contact time or impact time during the collision. Okay, during the collision. I'm not sure if my collision spelling is correct, or now accident. Okay, the first thing is that the airbag increases the contact time. Very important. First one mark comes here. It increases the contact time. Okay, during the collision again. We make a full stop for now. Then say, again, now you have stated that the airbag increases the contact time during the collision. Okay. Therefore, the second point that you want to mention out is that now, according to Newton's second law in terms of momentum, which is stated like this, according to this, with the same, remember what is it that I said we want to keep constant? The momentum. With the same or constant momentum, or for the same or cons yo constant constant, okay, According to Newton's second law in terms of momentum, we can write it like this. According to F net is equal to change in p divided by change in time for the same or for the constant change in momentum. Sorry, for the English in there, change in momentum. Now I repeat, the airbag increases the contact time, okay, during the collision. According to this, F net is equal to change in p divided by change in time for the same or constant changing momentum. Okay? What will happen? If this is constant, okay, and this one now has increased, what will happen to our net force? Now we say, therefore, the net force. Can you see? I'm not saying the force, the net force will decrease. Okay? Okay? Or there will be smaller net force experience. You can write your proper English. Therefore, the important part is that the net force will decrease. Since what? Since now F net is inversely proportional to changing time. Okay? Therefore, less damage will be caused. Of course, the damage will be there, but it will be less. Now, the first mark is that the airbag increases the contact time. And now we want to keep the same momentum, okay? Therefore, what will happen? Our now experienced net force will now be below, okay? Yes. Important lines talk about the what? First one, second one, third one. First one, you talk about changing time, increased. Now for the same change in momentum, now your F net will decrease. So now you can also make an example on the cricket one and say now as the maybe they will give you the name the wicker. Maybe let's say it is a wicker. As the wicker moves the hand backwards, now the wicker increases the contact time, right? Therefore, for the same change in momentum, therefore the net force experienced by the wicker will be less. Just like that. Just like that, just like that. These are they like to call it a high order question, but it is not. It is just your free 3 marks. Okay? It will just be your free 3 marks. Now, we see now that we have our formula that is F net. Okay, now it's fine. Let's talk impulse. Let's talk impulse. Where is impulse? Okay. Now remember what is impulse. We're going to be defining impulse in terms of physics, not just from Wikipedia or ChatGPT or AI. Now we are saying an impulse, it is now the product of the net force acting on an object and the time it takes for the net force to act on an object. It will make sense right now. The first keyword is that it is the product of the net force acting on an object. Remember, the net force should act on something, and now the time it takes for that net force to act on an object. Okay, which now we call the contact time. Okay, You please use your exam guide for definitions now, day of going to exam. Now, if I were to take off now the formula from this definition, it says to me impulse, which is going to be represented by I, it is equal to the product. Remember, the product is multiplication of the what of the net force and the what and the time. So it means now impulse will be what? F net changing time. This will be my impulse. Let me just write it in full. Impulse is equal to F net changing time. But I want you to see something. Okay? I want you to see something. So let me just say this is F net. Remember, it is measured in newtons. And now this is time. It is measured in seconds. So now it gives us that our impulse will be now newtons second, like that. Not newtons per second, newtons, big N, per, so not per, newtons second, okay? Now, I want you to see something. If I were to say F net change in time, it is equal to what? Remember what is F net equal to? F net it is equal to what? MA, okay? F net it is equal to MA. But now, what is MA equal to? Remember, MA it is equal to change in, okay, F net is equal to MA, then I still have to divide by changing time, multiply rather by changing time. But what is MA? Remember, rather A. It is now the rate of change of velocity. I'm still multiplying here by changing time. But can you see now my changing time here and my changing time here will cancel. Now I'll be left with what? With M changing V. But what is this? This is changing momentum. So what does that tell us? This tells us that F net changing time, which we now refer to as impulse, is equal to what? Equal to changing momentum. So now we can also get that from deriving this. Can you see if I multiply this time to the other side, it gives me F net changing time is equal to changing P. But now I wanted you to understand very well, okay? So now we have a formula that you're going to be using that says now F net changing time is going to be equal to changing momentum. Whereas this one, it is an impulse measured in newtons second. And this one will be now change in momentum. Measured in what? Kilogram meters per second. Now you can use now the SI unit interchangeably. What do I mean by that? You can use Newton second, kilogram meters per second for this one. Since well, they are equal, but now it will be advised, especially from me, that you use the correct SI unit for everything that you calculate. Very nice, right? Yes. So now it's very important that you take note that the change in momentum, it is very, very dependent on the what? On the F net. Okay? Yes. It is very dependent on the F net. And they are what? Remember, changing momentum, it is a vector. So as impulse is a what? Is a vector. Okay? Yes. Now I don't think I have time for examples. What I want you to understand now, it is a concept, okay? Because we'll do question papers. I prefer question papers rather than just basic examples, I'd say. Now we just said now impulse now is dependent on or rather momentum is dependent on F net, right? So now we have a graph of momentum, okay? Let's see now the graph shows the the following graph that I'm going to draw will show now the force exerted on the hockey ball over time, right? So let's say we have now that very nice graph and say here we're going to be having time in second, and here we'll be having now F in newtons. This will be the force now exerted on the, yes, on the whatever. Then let's say here from here to there, then coming back. Okay, this is not a nice one. Good. Now, let's say now the force that is exerted thereof, it is 150 newtons, okay? Let's say it starts from stationary and then the contact time thereof will reach 0.5. Actually, it's not necessarily the contact time, okay? But it is. But now, can you see now, here the force, what's happening to the force now here? Can you see that the force from zero, the force increased from 0 to 150 newtons, where it reached its maximum force, okay? On this case, what happened? It happened that maybe the ball was returned back, okay? The ball was returned back, okay? Yes. So now, if now, let's say, oh gosh, if now let's say that mass of the what? Mass of the hook, it is now 150 grams. Okay, let's see now the mass of the hook, it is 150 grams. Now let's try to calculate. Sorry, let's try to calculate the magnitude of the impulse. Now, I want you to see something. The area under the graph, area under the graph, area under the graph. Under the graph, in actual fact, it represents now the change in momentum, or rather the momentum. It is now the momentum. Every time when you say, sorry, not momentum, the impulse. When we say impulse, we will now represented it by that. Okay? So it will be that. But now, let's make an example, a calculation rather, and say now impulse, we're going to be using what? Area, okay? Remember, this is area under the graph. Which graph is this? Or under the graph, yes, the graph, it is a triangle. So we're going to say it is half multiplied by breadth, multiplied by now, by perpendicular height, okay? Or just height. Then we'll say, okay, this is a half. What is my breadth? My breadth is from here to there. It is 0.5 seconds. Then now, what is my height? Can you see that my height, it is now 150 newtons? 150 newtons. Okay, let me just do substitution of units here so that you see seconds. Then I'll multiply that, sorry, by what? By 150 what? Newtons. So we agreed that now this will be something like now 1 divided by 4 multiplied by 150, it is 75 divided by 2, now 37.5 what? Newtons multiplied by second. So it is Newton second. So I want you to be aware of this graph now thereof, because now it can appear maybe on multiple choice or maybe exam type of question where they say now maybe now the following graph shows the force exerted on a hockey ball over time. The hockey ball is initially stationary and all of that scenarios. Okay, so yeah, this is basically that when you now need to do what? To calculate the impulse. Now I'm gonna be moving now. Okay, either way, I'm gonna be doing momentum in impulse in one video. If it takes 3 hours, I'm sorry, but yeah. Now I'm gonna be now talking about conservation of momentum. Why? Because now I just realized that we've been talking now about the ball moving from the kicker and kicks the ball to the wall now. But now we've now been doing what? We've been now ignoring now what? Friction. Okay? We've been now ignoring what? Friction. And now, if now we ignore friction, we should now give it a proper term for ignoring that friction, right? So now let's talk of conservation of linear momentum. Okay? Conservation, not conversation, conservation of linear momentum. They can say momentum or linear momentum is still fine. Okay? What does it say? The definition says now, remember, when you conserve something, it should be in an isolated system. That one you should remember. Okay? So we are going to say the total linear momentum, please make sure that you use an exam guide for your definitions or the one that your teacher gives you. The total linear momentum where in an isolated system. I'd prefer you to use is conserved. Because now we are what? Conserving the linear momentum. Or instead of conserved, you'd rather say is conserved or remains. Okay, you're gonna write either of these, remains constant. The one that you feel like you are used to it. So now the important part is that the total linear momentum, the total linear momentum, where in an isolated system is conserved, or rather remains the same. What do I mean now? And before I move anywhere, I now want to explain now what exactly do I mean now by isolated system. Okay? I'll be in a position of saying, okay, I'm curious exactly what is an isolated system. What is that? What do you mean by that? Remember, just think of it as now when we say someone should be isolated, it means that particular someone should be just alone, okay? So what do we mean? We mean now it is a system. It is an isolated system. So it is It is a system. We start defining by saying it is a system. Okay? A system on which now the net, very important, net external forces are equal to 0. Or a system on which the net external force is 0. What do I mean? Remember, what do you mean about external forces? What exactly are external forces? I'll name them here. Applied force, tension force, frictional force, whether it is kinetic or static friction. Just friction, okay? I'll just write it friction. So this is what we call now external forces. So it means now when we conserve something, it means now we make it in the absence of those external forces, which we now name applied force, tension, or frictional force. Remember, you can also call them what? Conservative force. Okay, as you do work energy and power, we'll now call them actually non-conservative forces. Okay, yes. Now, from this definition that says conservation of linear momentum, it means now the momentum that we had initially or before, whatever the collision or whatever the case, is going to be now equal. Okay, it's going to be now equal to the change in momentum. Okay, after the collision, meaning now there was no change in momentum. It means now the momentum remained constant. Okay, so now I'll say the formula that we're going to use for conservation of linear momentum will say now the sum, okay, of momentum before or initial is equal to the what? The sum of momentum before and after. You can use the words instead of before, initial, and final. That's still acceptable, okay? Please do not do sigma like this. I people like at sigma. No, this is not even sigma. This is either EMF or E or whatever the letter in English. So please, sigma, try. You don't need to be like this precise. Even if you do this, you are in a rational exam. Can you see this is sigma? I am not these things of yours, people. I'm pleasing you. Okay, I want us to talk about conservation of a momentum a little bit now. I like to explain things and now using theories. Okay. Assume now you are, um, I want a perfect example. Okay, okay. Assume now that you are a soccer player, okay? I'm sorry for girls for using soccer now and then, okay? I'm not being biased, stereotypic, or whatever the word, but I'm just trying to make the theory now to be understandable. Let's say now, okay, I'm having now, let's not use a penalty because some don't know. Okay, a ball that is stationary, okay? A ball that is stationary like that. Mm, oh, okay. Let's say now I'm having a ball here, okay, that is stationary or at rest. This is before, okay. Then now I have another ball that's going to that, approaching that ball with a certain velocity. So you agree with me that they're gonna collide before, then they will be before, they will be during, which we don't necessarily care about for now. During it is when now these two balls do what? They collide. Okay? They collide. What we are interested in, it is after. After. After the collision, let's say now this ball comes to rest. Let's call this M1, M2. Then it comes to rest. Sorry, rest. And now M2, since when it was hitting, is going to move in that direction with speed V. Can you see now momentum is conserved because this speed here was transferred to the other, so this was supposed to be M2. This speed here was transferred to M2, whereas now M1 came to rest, and now M2 took the velocity. This is what we refer to as what? As isolated system, and now the conservation, the linear momentum is conserved. If there was friction, we all agree that this velocity will not be the same. Because why? This will not reach this a ball with the same velocity, because as we move in a friction rough surface that has friction, the velocity decreases. So hence now we are saying, okay, it's fine. Let's now make our system to be isolated. Now I want you to teach you very nice things. Remember, I'm here to teach you very nice things. Okay, yes. We have three types of collisions, in which we have two, in which I refer to as collisions, and the last one that I refer to as explosion. Okay? Okay. Let me now talk about collisions. Let me talk about collisions. I'll talk about oh, okay. Now I'm sorry, I have to show you how we manipulate this formula. We say now, okay, in this formula, the change in momentum before. Remember now that we are okay, okay, okay. On the impulse, we are now talking about. Remember, changing momentum, it is only about one object. Remember, changing momentum, it is a change in momentum of only one object. Now, when we talk about now a conservation of linear momentum, we are now talking about two objects. Okay, where can I move this? We are now referring to two objects. that will collide. Remember, for a collision to happen, we need two objects. So now it means now we will have what? We will have, let's say, momentum of A before. Okay, I'll use initially, okay? Momentum of A initially plus momentum of B initial. It is equal to what? To momentum of A final plus momentum of B final. So this is what we mean when we say we are conserving the system. The system is now conserved. It means now their initial momentum will be exactly the same sorry, it will be my English data is running. We are saying now the initial momenta. Okay, if we have two momentum, if we have one, it is momentum. If we have two, it is momenta. The initial momenta of these two balls will equal now the final momenta of the two balls. Now it means when I add this and this, it will give me the same amount as I add this and that. Another NB, direction is very important. Remember, we're still talking about what momentum here. So now, what will be now the momentum of ball A? We'll say now the momentum of ball A will be mass of ball A, velocity of ball A initial plus mass of ball. So just you need to indicate them like mass of A, velocity of A initial plus mass of B, velocity of B initial will be equal to now mass of A, velocity of A, but now it is final, plus mass of B, velocity of B final. So now this is what we're going to be using most of the time. Most of the time we'll be using this formula. It comes from where? From this. Okay? It comes from that. I think there is something that I'm gonna be okay. It's fine. It's fine. It's fine. We'll deal with that. Okay. Yeah. I'm gonna explain collisions as well as their graph. Let's have case one. Let's have case one now, where we have. I want you to take note of something. Where we have mass A. Okay. Let me just call this A. And now maybe ball B or object B. Okay. Let's say this one moves with that velocity going in that direction. Okay. Choice of direction will be very important. So we'll be using this coordinate system here. Okay. We'll be saying east, west. So anything goes to the east or right will be positive, west will be negative or left. So it will be going to east with a velocity of v. And now let's say now, just say VA, then V of B, let's say it is now at stationary. Okay, yes. Let's say now the collision happens now. Yes, the collision happens now. The collision happens. Okay, let me try that one again. Collision happens. Okay, now when the collision happens now, we have a case where now these two objects now move together as a what? As a unit. Okay, let me redraw that. We now have these two objects moving together as a what? As a unit, as A and B. And now, with whatever velocity they will be moving with towards that direction, we'll call that velocity of A plus B. Okay? It is they are both velocities. Now, I want us to create a formula for this one. I want you to have, every time when you have a scenario that you are told, you are able to draw it, okay? Now, here is this ball. Ball A has its momentum, okay? Its momentum with whatever velocity. And now ball B, block B rather, or object B has its momentum, which in this case it is 0, okay? This is before the collision. This was after the collision, okay? This is during and we don't care about it. Before, A had its momentum, B had its momentum, okay? We don't care if it was 0 or what, but they had their momentum, okay? But after the collision, after they collided, after the collision, what happened? They moved together. So it means now if they move together, their masses are now combined. But now what is it that they share? They share now the final velocity. Can you see now the velocity in which they are moving with? It is now the same. The velocity in which they are moving with, it is now the same. So it means now when we create a formula for this scenario, we're going to say now A had its initial momentum, similarly to B had its initial momentum. But now after the collision, what happened? They combined, they moved as a unit. Okay? They moved as a unit. So now we're gonna say, okay, if they moved as a unit, it means now their masses are now combined and they share what? The final velocity. This is the first type of collision that you might come across. Okay. Let's have the second scenario. So let's do that again. All right. Uh, let's, okay. Okay, now I'm back. Okay. I said let's create a second scenario, right? That was case one. Let's look at case two. I won't be doing calculations. I'm just trying to show you the type of cases you might come across. Case two. In case two, you might have now that the object had their initial momenta. Initially, they were moving in whatever directions. Let's say we are talking about cars now, or the trucks. I won't draw anything fancy. Let's say it was moving in that direction. This is still A with velocity of A. And now it's going to collide with now an object that was moving in opposite direction to it, okay? Now remember, if it is only like this, you won't see. I need to show you that now, okay, this one was moving in an opposite direction to that with velocity B, all right? Now, what happened after that? What happened after that? What happened after that is that, all right, there was what we call now collision. Collision happened. Collision happened, okay? This, remember, it is before. Remember this, what will happen now, it is what we refer to after or final. Now, final will say, all right, after collision, can you see now they are moving in opposite direction? They are coming in whatever respective directions they collide. Now, after collision, it is now taken that ball A moved, or rather not ball A, sorry, track A moved in opposite direction to that of its initial velocity or direction, sorry. So we are told that now after the collision, ball A, sorry, I don't know why I like saying ball. Object A moved in opposite direction that it was moving in initially. Same as now ball B is now moving in an opposite direction. Can you see? So this is now the type of collision that we might also come across. Now, can you see? Initially, they had their different momentums. I'll use momentums because when I say momenta, I feel like it will be a little bit tricky, but it's fine. We are learning a physics language. Initially, they had their momenta, independent momenta of this, okay? This one had its momentum, this one has its momentum. Initially, they had their momenta. After the collision also, can you see now this one had its momentum also, and B also had its momentum, okay, with whatever velocity there. Here, in case one, they had their momentum initially, but now finally they shared the momentum. Their momentum is for one single unit because now they combined. Okay, so now this tells us, okay, we can derive a formula and say, okay, initially they had their momentums, their momenta. Okay, that is different. Forget about the sign and what for now. But after the collision, what happens? They also had their different what momenta, because now can you see they did not combine, they did not do anything. Can you see about that? So this is B. Final. So they are just moving with their respective what momenta thereof. How nice. Let's move to case 3. Case 3. Case 3 now, it is almost similar to case 1, but now I want you to take note of it might happen, okay? It might happen that you get across such question. Let's say now you are having your truck moving in that direction thereof, all right? Let's say it is a van. You don't have time to be drawing here. It is a van moving with whatever, let's say this is A, moving with whatever velocity it is moving with, right? Then now, there comes a package of B from the sky. It is now dropped. Remember, they are very keywords. If something it is dropped, vertical projectile motion. If something it is dropped, now we are saying, if you haven't done vertical projectile motion, it's fine. If you have done it, you know when something it is dropped, its velocity, it is 0 meters per second. Okay? Yes. In Grabo, I'm recording the video, but you can come and stay. Yeah. No, it's fine. Good. No, it's not a call. I'm recording a video. That's something you can see. Make it. No, I said it's fine. No, I feel. Well, we'll talk. I guess I'll come to you. No, I want you to ask me. Like you're gonna talk in them. You wanna talk about this? No, it's a question. You wanna talk about? I want. Ask me. You? Do you? You trust me? You trust me? He said you make Pinky promise. I believe it. Pinky promise. You never say you make Pinky promise. Cool, Karafi. Okay. Velocity A moving in that direction. Then a ball is dropped now. Then now what will happen? Remember, there will always be collision thereof. After now, an important collision. So what will happen is that this ball, this object that was dropped from the sky or wherever, will now, what's the proper English? Will now stack into the van there. So we'll be having something like, I'm tired of throwing you. Okay, we'll be having something like this, but now with what? With ball B. Please remember this is A. With object B here. Okay, we have object B there. Now, can you see now they are now moving as what? As a unit with whatever respective velocities thereof. So we'll say this velocity will be the combined velocity of them both. Okay. So now this one is also the same scenario where we say, okay, it will be mass of A, velocity of A initial plus mass of B, velocity of B initial. It will now equal to what their combined masses, because now they are combined, right? Multiply by their final velocity, which is now same. I want us to move now to what we call explosion. Explosions. You have an idea when something explodes, it was initially a compact, or it was initially a unit, but after collision it breaks apart into pieces. Okay, so that is the idea that you will be having, or rather you have, about now collision, right? So now let's say we have let's say now we have, let's say, case one. This is case one under explosions, right? Let's say now you have a mass. This one, they like it on multiple choice questions, is fine. Okay, let's say now you have an object that are held, objects that are held together by a spring. They are held together by a spring. Okay, A, B, and say, let's say now their velocities, it is 0. Okay, remember now, it is their both velocity, okay? It is 0. Then now after explosion, or a push, or whatever thing that will happen there, I'll just call it explosion. After the explosion, now what will happen? What will happen is that, okay, they will now move in different directions. Okay, let's say now, ball A, so the object A pushes now ball B forward. Okay, so ball B, we know that object B will move in that direction because it is now pushed, right? But now what will happen to ball A? It will move backwards. Why? Now we are now in a position of applying what we call now Newton's third law. Remember, when two things collide, I've been ignoring this, but now it's time to mention it, now that we are talking about what are these? Now that we are talking about what's this? Explosions. When two objects collide, there is a force that is applied thereof. Okay. Now remember, if ball A apply a force on ball B will exert the same force, but of what? Of equal magnitude. Okay. But where? In the opposite direction. Therefore, now that's where we say now momentum is also a topic that is composed of Newton's second law, but it's also now composed of what? Of Newton's third law, because now I'm saying when objects now collide, they will exert a force on each other. The force will be equal. But now, the thing is that, okay, let me tell you just a reality now. When someone is hit by a car, okay, let me not make that a bad example. Sorry, if it has been traumatic to you. Let's say now, okay, okay, let's say now, I'm sorry for this example. I know it's a bad one, but yeah, since when we are dealing with cars and what, let's say now a car, a nice car, and a truck collides. Okay, collide. Now the force that the truck is exerting on the force that the truck is exerting on the car, it is the same force that the car is exerting on the truck. But now, since their masses are not the same, the one that is smaller will experience the what? Greater acceleration. Remember, the formula says F net is equal to ma, but when I derive that in terms of acceleration, I'm going to get F net divided by mass is equal to acceleration. So now, the F net, let's say is the same. The F net is the same, okay? So now if the mass is smaller, remember the F net is the same for both of them. If the mass is smaller, the acceleration will be great. Hence, this one will experience higher damage, or this one will move in the opposite direction, whereas this one will just move a little bit backwards. Okay? Can you see it moves a little bit? Why? Because now its mass is what is greater, therefore causing the acceleration to be less. Okay, so this is the things that you need to understand. Also, remember what is F net changing time. Okay, their F net changing time, which is their impulse, will be now the same, but it will be what in opposite direction, because now the contact time is the same. Okay, contact time is the same, their force is the same. So it means now their momentum, their what's this? Their impulse will also be the same. Okay. Similarly, their momentum, we just said it will be the same. So whatever this momentum it experiences towards that side, this one will experience towards that side, or let's say opposite direction, like that. Okay. So yes. So here it means now if I create my scenario, it means now, okay, they will start off initially being nice, cool, together with initial velocity, but now in finally, they will now be moving in separate ways, which is final, mass of B, velocity of B. Now this will be final. That's the case. The last case that we might consider, it is now a gun. I'm sorry, I'm gonna draw case 2. This is case 2 of collision. A rifle. Let's consider a rifle. I don't know how to draw a rifle, but yeah, I'm gonna outdo myself. Okay. And now, let's say now, within that rifle, we have a bullet inside. We know, of course, we are in a war here. We are fighting against physics. Okay. Let me just label that as a bullet. This is a rifle. Okay. Or a firearm. I don't know. I'll just call it a rifle. I don't know how to even spell a rifle. Or a firearm. Let's say firearm. Discharge of firearm. Now, can you see that initially, okay, what will happen? Let's say there will be a shooting, okay? After a shoot in which I consider a collision, remember initially they are at rest, okay? Initially they are at rest, the velocity of the bullet and the gun. Okay, why don't you call it a gun? They'll call it nicely in an exam. Gun. The velocity of the bullet as well as the velocity of the gun, initially they are zero, because if they are in your hand like that, pointing at that particular person you want to shoot or whatever the case, can you see they are stationary like that, focusing? Okay. Now they are stationary, it means their velocity is zero. But now after, I want you to, this is practical, I want you to make physics practical. After shooting something, what happens to the gun in your hand? Do you agree with me that your hand goes backwards a little bit? This is what we call your hand will recoil. Okay. After shooting, your hand will sorry, the gun will recoil, meaning it will move backwards. Okay. The gun will move backward. Okay, it's now a bigger. The gun will now move in an opposite direction, will move backwards. Okay, velocity of the gun. This is what we call recoils. Okay, when it recoils, it means it moves backwards. Okay, and now, but tell me what will happen to the bullet? Oh, the bullet is sprinting. The bullet will now move with a very high speed thereof. Okay, this is a very bullet a very dangerous bullet moving in that direction with a very important speed thereof, targeting that particular person, a criminal thereof. Okay, so this is the case that will happen there. Okay, yes. So this is the case that will happen. Now, can you see that initially we had the mass of the bullet plus the mass of the gun, okay, and their initial velocity, and now finally they moved in different directions. Mass of the bullet, velocity of the bullet, initial, sorry, final, plus mass of the gun, velocity of the gun, final. So this is what happened there. Important. During a collision or explosion, I'm not sure where is my spelling wrong. I think my explosion is correct. Explosion. There are three things that will happen. The force of A, the force that A will exert on B will equal, but in opposite direction to the force that B will exert on A. Let me say force A on B will equal to negative force B on A. This is where we apply what? Newton's third law. Another thing that might happen now. Let me see. Okay. Another thing that might happen is change in momentum of A is equal. Remember, change in momentum, we are talking about one object, is equal to negative change in momentum of B. Another thing, impulse of A is equal to negative impulse of B. So these are very, very important things thereof to happen. Whereas now, remember, change in time for A is the same as change in time for B. Now, because the change in time in which the collision happens is the same, right? Yes. Now, one thing I want you to take note of is that their change in momentum will be opposite in direction. They will be equal in magnitude, but opposite in direction, right? So that is the very, very, very important thing that you should be aware of thereof. Okay, yes. Now, I don't want to talk more about what now, but we now have something that we refer to as now elastic and inelastic collision. Okay, let me remove this. Okay, good. Thank you. Types of collision. Okay, we've been talking about collisions, right? Now we have types of collisions, and not cases, types. Okay, we now have this one that we refer to as what? As elastic collision. That really happens in our daily life situations. What is now an elastic collision? An elastic collision will refer to a collision, okay? A collision in which, okay, I did mention that there's something, oh, okay. A collision in which, the what? In which both, very important, momentum and, actually not momentum, both total momentum, a collision in which both total momentum momentum and total kinetic energy are conserved. Conserved. Okay. What do you mean? Remember, okay, in these two types of collisions, momentum will always be conserved, okay? But in this case, we say collision in which both, very keyword, both total momentum and total kinetic energy are conserved. Very important, both. What do you mean? Okay, remember in this case, momentum is conserved, okay? That will always be the case. But now the interesting part is that the sum of the kinetic energy initial, it is equal to the sum of kinetic energy final. Now, what do we mean? Remember, initial, if you have speed and you are a particular person with mass, you are having kinetic energy, right? So now we are saying the kinetic energy, okay, which will be now, remember, let me just remind people, it's either you write it as EK, or let me write it here, EK or just K, it is equal to what? Half mv squared. This will be now the sum means between the two things, okay? So this will be half m a v a initial mass of A and initial velocity of A squared plus half mv v initial squared. Now we are saying it only for only for elastic collision. It's either you are told or you are required to prove whether it is elastic or inelastic. Okay? It is equal to what? It is equal to half MAVA final squared plus half MBVB final squared. So this is what we mean now by initial sum of kinetic energy initial is equal to sum of kinetic energy final. Now let's go to what we refer to in inelastic collision. Okay, now energy can be lost in different ways, okay? Energy can be lost in a form of sound, in a form of heat, in a form of whatever, okay? Yes. So we are going to say in this one, it is a what? A collision in which only total momentum is conserved. Conserved. A collision in which only total momentum is conserved. What do we mean by that? We mean that, okay, the total momentum is conserved. Okay, remember, if it is conserved, they are equal, but you don't need to state this. Kinetic energy before is not equal to, is not equal to kinetic energy final. So this is what we mean in elastic collision. Remember, it can be lost in three or two different things. Through heat, through sound. Okay? Yes. Mm-hmm. Sound and heat. All right. All right. Now, I want us to have just a one example and see now if now our momentum is conserved or not. Okay. You might have now a scenario that says, okay, this is the last part. I'm done. I'm done. This is the last part. Okay. This is what you're gonna do. Okay, let's have an example. This is very important because people lose marks, unnecessary marks by doing this thing. Okay, let's say the velocity. Okay, it's fine. Instead of writing the scenario, it's fine. I'll just draw. A is moving in that direction. Okay. With velocity. Okay, remember a coordinate system. Okay, important. East, west. Remember, we are dealing with vectors here. Going to east or right, depending on what the examiner gives you, this is positive, this is negative. With a velocity of 5 meters per second. You can also choose west as positive and sorry, east as negative is fine, but this is B. It's moving in that direction with a velocity of 3 meters per second. Then after the collision, let's say they collide, and what happens? What happens? Let's say, okay, this one moves in opposite direction with a velocity of 2 meters per second. Okay, I don't think 2 will be good. Ooh. Yeah, let's use 2 meters per second. Now, let's find the velocity of B. A, B. Find the velocity of B. Okay, let's find the velocity of B. Now, let's say the mass here. And this one has a mass of 1 kilogram, okay? Yeah. Now, let's find the velocity of B. How can you do that? Now, I'm told that, okay, can you see now? Initially, I want you to see this. Initially, they have their different momentum. So we'll say, okay, it's fine. Initially, they had their different momentum. Okay. Finally, what happened? Did they move as a unit? No. Why? Because this one moved in that direction and this one is unknown. Okay. So they did not stick together like that. So it means now, okay, it means A had its final momentum, and similarly to B, it means now it had its final velocity. Now, it will be beneficial for you to come here and say, okay, this velocity is positive, this one is negative. This is 3, by the way, not 8. Why? Because we chose right as positive, okay? So, and come here and say, okay, this one will be negative also, so that when you substitute, it becomes easier and nice, okay? Now, let's be in a position of doing that. We're going to say, what is mass of A? Mass of A, it is 0.5, velocity of A, positive 5, plus mass of B, it is 1, velocity of B, negative, moving in that direction. It is equal to 0.5 multiplied by negative. Can you see that? 2 plus mass of B, it is 1 multiplied by velocity of B. I'll say velocity of B final. Okay. When they say calculate the velocity of B, it means you have to give out direction as well as, the magnitude as well as direction. But if they just say calculate the speed of VB, we do not care about the direction. Okay. We only care about the magnitude. Okay. Therefore, let's do math. Let's say this is A. Okay. A, find B final. Okay. Let's say we have that A instruction there of and okay, let's do our math there. This is going to be 0.5 multiplied by this is going to be 2.5 minus 3. It is equal to -1 plus VBF. Then when I take this to the other side, it's going to be 2.5 minus 3, it is negative 1.5, 0.5 plus 1, it is 0.5 is equal to VF. Therefore, you'll say VF is equal to 0.5 meters per second. The answer is positive, so it's going to be west. So, where east or right. If the answer was negative, you're going to say now it's moving where west. Okay. This is if they want what velocity. If they want speed, you'll say therefore VF is equal to 0.5 meters per second, or just say speed is equal to that answer. Even if you got negative here, but if they want speed, you'll say for therefore speed is equal to positive that answer with no direction. Let's say B, they say to us, is the collision elastic or inelastic? Proof with suitable calculations. For 5 marks. 5 marks. This one for 4 marks. Okay, so how do we mark this? A formula, substitution on this case, substitution on this case, and now respecting that they wanted velocity with a direction, 1 mark. Okay, yes. So now let's consider that. Let's see. Is the collision elastic or inelastic? When you prove, you do not start by saying sum of kinetic energy initial is equal to sum of kinetic energy final. This is wrong. Do not start like that. When you are proving, you are trying to see if they are equal or not. What your first step is calculating the sum of kinetic energy initial will equal to what? It is half MA VA initial plus half MB VB initial. You do not know if the sum of kinetic energy initial is equal to that now. You are not told. You are trying to prove that. Okay? So you come here and say, okay, this is a half. What is mass A? 0.5. Velocity of A, it was 5 squared, sorry. Okay? Half mass of B, it is 1. Velocity of B, you can put the sign negative because this one is speed. Okay? In kinetic energy, we consider the speed because kinetic energy does not care whether you're moving to the right or left, as long as it is an energy. Okay, so but for purpose of good practice, you'll say -3 squared. Was it -3, right? Yes. Then how much does it give us? So this is 25 divided by 4. 20 divided by 4. Okay, let me just use my calculator and stop being stubborn and making myself a mathematician here. 5 squared plus 0.5 multiplied by 1 multiplied by now 3 squared. I get something like 10.75 joules. Remember, kinetic energy is measured in joules. Now you come back and say, okay, let me see how is my kinetic final. I'm trying to confirm. Okay, I'm gonna say, okay, let me just change the color here. For sum of kinetic energy final, I'm gonna say, okay, this is half MAVA final plus half MBVB final. So when I substitute, it is a half, mass remains the same, velocity became -2, can it? Yes, -2, then square that. Sorry about forgetting the square. Do not forget that square. If you forget the square, you lose 1 mark for formula. And if the formula is incorrect, I don't know how you're going to substitute into that. Plus half 1, then we say the velocity thereof we found is how much? Is 0.5, okay? Squared. So it's just a matter of punching that one again into a calculator. Okay. Then I get something like, if I'm wrong, it's 5. I'm sorry, 1.125 joules. Now, can you see now that, can you see number 3? Number 3 is us concluding now that the sum of kinetic energy initial is not equal to the sum of kinetic energy final. Okay? Can you see now this was 10.75, this is 1.125. Can you see now that the sum of kinetic energy initial is not equal to the sum of kinetic energy final? Which condition satisfies this? Which type of collision is this? Then you therefore say, therefore, the collision is inelastic. Done. You are proving. First mark, it is for formula. Second mark, substitution. Second mark, substitution. Okay, this substitution into initial velocity, initial kinetic energy, 1 mark. Kinetic final velocity substitution, 1 mark, because formula already given there. Okay, then you seeing that the kinetic energy, the sum of the kinetic energy initial is not equal to the sum of kinetic energy final. You have to tell us this. It is another mark. Therefore, stating and answering the question that the equation is inelastic is another mark. 5 marks. Can you see how easy those marks are? Yes. So yes, that's all about what's this momentum and impulse in just one video. Okay. So I think I did my best here to try and explain this in how many slides? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I think 8 is a good number. Okay. So yes, these are very important for you to take what notes. Can you see now? I did not involve many calculations because now I want you to understand what the concept before. Okay, I wanted you to understand the concept thereof. All right. So yes, I want to believe now you are in a position where now you understand your theory very well. All right. I'm in a position in which now I want to believe now that you understand the the theory very, very well. Okay. So now, if that's the case, I want to believe now everything it is in place, and you're gonna be passing now momentum and impulse. What will follow is now question papers. Okay. Question papers based on momentum and impulse. I hope you enjoyed now the video with me on momentum and impulse. I know it may be long, but yeah, it is worth watching. Okay. Yes. Graphs. I'm gonna make a video. Okay, actually no. Before I say I'm going off, let me show you how graphs are interpreted. Okay, let's just interpret graphs. Now, I want you to take note of something. Let's say we are having object A. Actually, let me just do this. Let me do this. Okay. Let's say this is velocity in meters per second. This is time in seconds. Now we have object A. Okay. We have now object A moving with a constant velocity of, let's say this is 5. Object A moving with a velocity of 5 meters, okay? In the positive direction. Can you see now this is a positive direction? And now we also have now ball B moving in the opposite direction. So let's say this one is moving towards east. This one is moving towards west, okay? In opposite direction. Now they are moving again. Now they are moving towards each other, right? So they will collide. Now this is what we call, they will do what? They will collide. Okay? This should be equal here. They will collide. They will eventually collide at a particular point, and then after collision, let's say they move as a unit. The first one is this scenario. I want you to, this is A, then let's say this is moving at -2. This is A, this is B, okay? Then this is A plus B. I want you to see that if this graph is given to you like this, okay? This part here, okay, let me indicate this by times, okay? Let me indicate this by times, okay? T1, T2, then, yeah. Now, between between 0, okay, let me say T0 instead. Between T0 and T1, we have what? We have, let me charge on my laptop, okay? Okay, I'm done. We have before collision. It is before collision. During this moment here, here, it is before the collision here. Why? Because can you see they are moving in separate ways, okay? In different ways. But now, from T2, sorry, from T1, let me say from T0 to T1, and from T1 to T2, it is during. This is during the collision. Then from T2 going forward, it is after the collision. Now, it means now this time, the time difference here. Okay, so we said here, here, before, during, let me do this. This is before, and this here it is after. Okay? Remember, they are moving with a constant velocity. Immediately they collide, now there will be a change in their velocities respectively. But now, this is the case in which now, I want you to know how to interpret graph. This can be velocity or momentum. Either way, velocity or momentum, either way they have given you. Now, let's interpret this in terms of drawing. Can you see now this? You can say, okay, we had object A moving in that direction with 5 meters per second, and object B moving in that direction with 2 meters per second. And after the collision, what happens? Can you see now they have combined? So it means now, and can you see now they are moving in the upper boundary here in the positive values. So it means now A, and let's say here the velocity is, or let's say they want you to find it. A and B are moving together in a positive direction. Can you see? This is in a positive direction. Therefore, this is what we call, this is the first graph that you come across. The second graph that you might come across, it is now where you have, okay, I'll be quick on this one. I won't be precise, okay? The examiner knows how to be precise. It's moving with this velocity there. Similarly, this is moving with that velocity there. You agree with me that this is initial velocity? Okay, let me say, I'll repeat the 5 and -2. That's fine. Then Remember, this is during before the collision, okay? Then after T1, they're off, they come into what? Into collision. They come into collision, okay? And the collision ends at T2. Then after T2, I want you to see something. This one continued and moved in that direction. This one then continued and moved in the opposite direction. Now, what happened here? Let's say this one now has a velocity of, okay, it's not realistic, but positive, or maybe. Then this one maybe has a velocity of, here, -1. Okay? Yes, I think the graph is more or less like this, if I'm not mistaken. Yeah, it's like this. Yeah, if I'm still correct about it, okay? Yes. So yeah, it's like that. So it shows you, okay, this is object A, object B, and this one was moving in a positive direction. This one was moving in a negative direction. But now after collision, this is, I repeat, this part here, it is before, okay? This part here, where they start to cross, it is during. Then the rest part from here going there, it's after. Okay. They can ask you about momentum. Let's say calculate the momentum, or rather, calculate the net force acting on these two objects. If now the yeah, calculate the net force acting on the object. Now the net force, remember, you take it from F net, change in time is equal to change in P. Okay. Let's say they say calculate the F net that A experiences. Okay, F net that A experiences. So remember, it's going to be F net. Then the change in time will be T2. You're going to take the time of during. Okay, the net force, remember, occurs during the collision. So it's going to be what? T2 minus T1. Therefore, mass of A, velocity of A final minus velocity of A initial. Then you do your calculations, you get your net force. Okay, yes. So this is basically that about the graphs. You being in a position of knowing, oh, okay, if it is moving like this, it is initial. Okay, let me do that. If it is moving like that, it is initial. Like this, there are initials here. Then here, it is what we call during. This is during the collision. Then we have what? After the collision. So I want to believe that you are following, folks, and everything that I've tried to explain there, it is now explainable thereof. Okay, so yes, thank you very much, folks. Until we meet on the next video. Thank you.